Gas giants such as Jupiter, Saturn, Uranus, and Neptune dominate the outer reaches of our solar system. These colossal planets, composed primarily of hydrogen and helium, boast atmospheres filled with swirling storms and tempests of unimaginable scale. Among the most notorious features of these gas giants are their massive storms, which can stretch across thousands of kilometers and rage for centuries. While these storms captivate the imagination, they also pose significant risks and consequences, the potential ramifications of a massive storm on a gas giant like Jupiter. Before delving into the consequences, it's essential to grasp the nature of these storms. Gas giants, lacking a solid surface, have atmospheres that support dynamic weather systems. The most iconic storm on Jupiter, the Great Red Spot, has endured for centuries and is larger than Earth itself. These storms are driven by complex interactions between the planet's atmosphere, internal heat, and rotational dynamics. A massive storm on a gas giant can disrupt atmospheric circulation patterns, leading to turbulence and changes in weather systems. This disturbance can alter the planet's climate on a global scale, affecting temperature gradients and wind patterns. Gas giant storms, like their terrestrial counterparts, generate intense electromagnetic activity. Lightning storms on Jupiter, for example, produce radio emissions that can be detected from Earth. Such activity may interfere with spacecraft operations and communications. While gas giants lack solid surfaces, the upper layers of their atmospheres can experience significant disturbances during storms. High-speed winds and convective currents can create visible features, such as dark bands and bright clouds, altering the planet's appearance. Gas giants often host extensive moon systems and ring structures. Massive storms can perturb the orbits of moons and cause disruptions within the rings. These interactions may lead to collisions, gravitational disturbances, or changes in orbital resonances. Gas giants are surrounded by powerful magnetospheres generated by their internal magnetic fields. Storms can influence the structure and dynamics of these magnetospheres, leading to increased radiation levels and auroral activity. This space weather can affect spacecraft and planetary exploration missions in the vicinity of the gas giant. Gas giants, with their massive size and powerful magnetic fields, create dynamic and captivating environments within our solar system. These magnetic fields, generated by the planet's metallic hydrogen interiors, extend far into space, shaping their surroundings and protecting them from harmful solar radiation. However, what happens when these magnetic shields begin to weaken or dissipate? In this article, we'll investigate the potential consequences of the depletion of a gas giant's magnetic field. Before delving into the consequences, it's crucial to grasp the role of magnetic fields around gas giants. These magnetospheres are vast regions of space dominated by the planet's magnetic influence. They interact with the solar wind, a stream of charged particles emanating from the sun, deflecting and trapping them in intricate patterns. Increased radiation exposure. Gas giants with weakened magnetic fields are more susceptible to solar wind and cosmic radiation. Without adequate shielding, this radiation penetrates deeper into the planet's atmosphere, posing risks to any potential life forms and affecting the chemistry of the atmosphere. Auroral activity. Gas giants exhibit spectacular auroras, similar to Earth's northern and southern lights. These luminous displays are caused by charged particles from the solar wind interacting with the planet's atmosphere. A weakened magnetic field can intensify auroral activity, leading to brighter and more frequent displays visible across larger regions of the planet. Atmospheric loss. The interaction between a gas giant's magnetic field and the solar wind forms a protective barrier known as the magnetosphere. Without this shield, the planet's upper atmosphere becomes vulnerable to erosion by the solar wind. Over time, this atmospheric loss can lead to changes in the planet's composition and density. Moons and rings. Gas giants often host extensive moon systems and ring structures. A depleted magnetic field can affect the dynamics of these moons and rings, leading to orbital instabilities, collisions, or disruptions in ring formation processes. Gas giants influence space weather in their vicinity through their magnetospheres. A weakened magnetic field can result in increased levels of radiation and charged particle flux in the surrounding space environment. This can pose challenges for spacecraft operations and planetary exploration missions. The formation of planetary systems is a delicate dance of gravity, gas, and dust, orchestrated over millions of years. Gas giants, with their colossal size and gravitational influence, play a pivotal role in shaping the architecture of these systems. However, the process of gas giant formation and migration is not without its risks. In this article, we'll explore the potential hazards associated with the formation and migration of gas giant planets within a planetary system. Gas giants typically form through a process known as core accretion or gravitational instability. In the core accretion model, a solid core gradually accumulates gas from the surrounding protoplanetary disk, eventually reaching a critical mass to initiate rapid gas accretion. In contrast, gravitational instability occurs when regions of the disk become gravitationally unstable, collapsing to form gas giant protoplanets directly. Disrupted orbital dynamics. Gas giants are often born in regions of the protoplanetary disk far from their final orbital destinations. As they accrete gas and interact gravitationally with the disk, they may undergo significant migration, moving closer to or farther from their parent star. This migration can destabilize the orbits of smaller rocky planets and other gas giants, leading to orbital resonances or even ejections from the system. Resonance effects. Gas giant migration can result in resonant interactions with other planets in the system. When planets' orbital periods become synchronized or locked in resonance, their gravitational influence on each other intensifies, leading to eccentric orbits and potential collisions. This phenomenon can disrupt the stability of the entire planetary system. Impact on habitable zones. Gas giant migration can alter the boundaries of the habitable zone around a star, where conditions are favorable for liquid water to exist on a planet's surface. If a migrating gas giant crosses the habitable zone, it may gravitationally perturb inner rocky planets, destabilizing their climates and potentially rendering them uninhabitable. Debris disruption. Gas giants migrating through a protoplanetary disk can stir up debris and smaller bodies, leading to collisions and fragmentation. This process can generate a cascade of impacts, further altering the composition and structure of the planetary system. Stellar interactions. In multi-star systems or regions of high stellar density, gas giant migration can be influenced by gravitational interactions with neighboring stars. Close encounters with other stars can perturb the orbits of gas giants, leading to unpredictable trajectories and potential ejections from the system. In the vast expanse of space, celestial bodies interact through the gravitational tug-of-war, shaping orbits and sculpting the dynamics of planetary systems. Gas giants, with their immense mass and gravitational influence, play a central role in these cosmic interactions. However, the gravitational ballet between gas giants and other celestial bodies can also lead to risks and consequences. In this article, we'll explore the potential hazards associated with the gravitational interactions between gas giants and their planetary companions. Gravitational interactions between celestial bodies are governed by Newton's law of universal gravitation, which describes the attractive force between two objects with mass. Gas giants, with their massive size and gravitational pull, exert a profound influence on the orbits and trajectories of nearby objects, including rocky planets, moons, and smaller debris. Orbital instabilities. Gas giants can perturb the orbits of neighboring celestial bodies, leading to orbital instabilities and eccentricities. Close encounters between gas giants and rocky planets or smaller moons can result in gravitational disruptions, altering their trajectories and potentially leading to collisions or ejections from the system. Tidal forces. Gas giants exert tidal forces on nearby objects, stretching and deforming them as they orbit. This tidal interaction can generate heat within the interiors of moons and other bodies, leading to geological activity such as volcanic eruptions or tectonic movements. However, excessive tidal forces can also cause tidal heating, leading to the melting of planetary interiors and potential structural instability. Resonant locking. Gas giants can induce resonant locking in the orbits of nearby moons, causing them to synchronize their orbital periods with the planet's rotation. While resonant locking can stabilize moon orbits over geological timescales, it can also lead to gravitational instabilities and orbital resonances, resulting in orbital eccentricities and potential collisions. Debris clearing. Gas giants act as gravitational vacuum cleaners, sweeping up debris and smaller objects in their vicinity. While this process helps to maintain the stability of the planetary system by clearing out potentially hazardous debris, it can also lead to collisions between gas giants and larger asteroids or comets, resulting in impact events that may have significant consequences for the system. Planetary migration. Gravitational interactions between gas giants and smaller bodies can induce planetary migration, leading to changes in the architecture and dynamics of the planetary system. This migration can destabilize the orbits of rocky planets and other gas giants, potentially leading to orbital resonances or ejections from the system. Gas giants, with their colossal size and mysterious interiors, conceal a furnace of heat and energy deep within their layers. This internal heat, generated by gravitational compression and residual heat from planetary formation, drives dynamic processes within the planet, from atmospheric circulation to magnetic field generation. However, what happens when these internal heating mechanisms falter or malfunction? In this article, we'll explore the potential hazards associated with the failure of a gas giant's internal heating mechanisms. Gas giants like Jupiter and Saturn derive their internal heat from multiple sources. Primarily, heat is generated through gravitational compression as the planet's massive bulk exerts pressure on its core. Additionally, residual heat from the planet's formation contributes to its internal energy budget. This heat drives convective processes within the planet, leading to the formation of complex atmospheric structures and sustaining its powerful magnetic field. Atmospheric collapse. Gas giants rely on internal heating to drive atmospheric circulation and maintain stability. If internal heating mechanisms fail or weaken, atmospheric dynamics may be disrupted, leading to the collapse of atmospheric circulation patterns. This collapse can result in the stagnation of atmospheric gases, altering the planet's climate and potentially triggering extreme weather events. Magnetic field decay. Internal heating is crucial for sustaining the powerful magnetic fields observed around gas giants. If heating mechanisms falter, the planet's magnetic dynamo may weaken or cease altogether, leading to the decay of the magnetic field. A weakened magnetic field exposes the planet and its moons to harmful solar radiation and cosmic rays, potentially impacting habitability and space exploration missions. Hydrogen-helium phase separation. In gas giants like Jupiter and Saturn, internal heating drives the separation of hydrogen and helium within the planet's interior. If heating mechanisms fail, this phase separation process may be disrupted, leading to the accumulation of helium in the planet's core. This accumulation can alter the planet's density profile and internal structure, potentially affecting its gravitational field and atmospheric properties. Storm intensification. Internal heating plays a role in fueling the powerful storms and atmospheric phenomena observed on gas giants. If heating mechanisms fail, the energy supply for these storms may diminish, causing them to weaken or dissipate. Conversely, localized heating failures may lead to the intensification of storms in certain regions, creating hazardous conditions for spacecraft and atmospheric probes. Planetary evolution. Internal heating mechanisms are intimately linked to the long-term evolution of gas giants. If these mechanisms fail, the planet's thermal evolution may be disrupted, affecting processes such as core differentiation and mantle convection. This disruption can have far-reaching consequences for the planet's internal structure, composition, and overall evolution over geological timescales. Gas giants, with their tumultuous atmospheres and ferocious storms, present a formidable challenge for space exploration missions. From towering thunderheads to hurricane-like vortices, these extreme weather phenomena can wreak havoc on spacecraft and probes venturing into their domain. In this article, we'll examine the impact of extreme weather on gas giants and the challenges it poses for space exploration missions. Gas giants, like Jupiter and Saturn, boast atmospheres teeming with dynamic weather systems. These planets exhibit a variety of extreme weather phenomena, including lightning storms, cyclones, and massive atmospheric disturbances. The most iconic of these features is Jupiter's Great Red Spot, a colossal storm larger than Earth that has raged for centuries. Electromagnetic interference. Lightning storms on gas giants produce intense electromagnetic activity, including radio emissions and bursts of gamma rays. These electromagnetic disturbances can interfere with spacecraft communications and instrumentation, posing challenges for navigation and data transmission. Atmospheric turbulence. Gas giants experience powerful atmospheric turbulence, driven by convective processes and jet streams. Spacecraft entering the atmosphere of a gas giant may encounter severe turbulence, risking damage to sensitive instruments and spacecraft components. Maintaining stability and control in such conditions is essential for mission success. High winds and pressure gradients. Gas giants have strong winds that can reach speeds of hundreds of kilometers per hour. These high winds, combined with steep pressure gradients, create extreme conditions for spacecraft descent and landing. Designing spacecraft capable of withstanding these forces is crucial for safe entry into the planet's atmosphere. Radiation hazards. Gas giants are surrounded by intense radiation belts generated by their powerful magnetic fields. Spacecraft entering these radiation belts are exposed to high levels of energetic particles, which can damage sensitive electronics and affect human health. Shielding spacecraft and minimizing exposure time are essential strategies for mitigating radiation hazards. Limited mission lifespan. Extreme weather and radiation conditions on gas giants can shorten the operational lifespan of spacecraft and probes. Harsh environments accelerate wear and tear on spacecraft components, limiting their ability to function effectively over extended periods. Mission planners must carefully balance mission objectives with spacecraft durability and reliability. Gas giants, with their vast atmospheres of hydrogen and helium, represent some of the most pristine environments in the solar system. However, the delicate balance of these atmospheres can be disrupted by external factors, including human activities and natural phenomena. In this article, we'll delve into the dangers of contaminating gas giant atmospheres and the potential consequences for these enigmatic worlds. Gas giants, such as Jupiter and Saturn, possess thick atmospheres composed primarily of hydrogen and helium with traces of other gases and compounds. These atmospheres are in constant motion, driven by convective processes, jet streams, and atmospheric disturbances. The composition and dynamics of gas giant atmospheres play a crucial role in regulating planetary climates and supporting complex atmospheric phenomena. Spacecraft debris. One of the primary sources of contamination for gas giant atmospheres is space debris from human-made spacecraft. Debris from satellite collisions, rocket stages, and defunct spacecraft can enter the atmosphere of a gas giant, introducing foreign materials and pollutants. This contamination can disrupt atmospheric chemistry and have long-term consequences for planetary health. Chemical reactions. Contaminants introduced into gas giant atmospheres can undergo chemical reactions with native gases and compounds, altering atmospheric composition and dynamics. For example, reactive chemicals from spacecraft materials or propellants can react with hydrogen and helium in the atmosphere, forming new compounds and potentially depleting essential atmospheric constituents. Biological contamination. If spacecraft carrying microbial life or biological contaminants crash into a gas giant, there is a risk of introducing biological organisms into the atmosphere. While the extreme conditions of gas giant atmospheres may be inhospitable to most forms of life, extremophile microbes or spores could potentially survive and proliferate, leading to unintended biological contamination. Natural disasters. Natural phenomena such as asteroid impacts or comet collisions can also introduce contaminants into gas giant atmospheres. Impact events release shockwaves and heat energy that can vaporize surface materials, injecting debris and volatile compounds into the atmosphere. These contaminants may trigger atmospheric reactions and affect planetary climate dynamics. Human activities. Future human missions to gas giants, such as atmospheric probes or robotic landers, could inadvertently contaminate the atmosphere with spacecraft materials, propellants, or waste products. Careful planning and adherence to planetary protection protocols are essential to minimize the risk of contamination and preserve the integrity of gas giant environments. Gas giants, with their massive size and tenuous atmospheres, are subject to processes that can lead to the escape of atmospheric gases into space. These processes, driven by factors such as thermal escape, solar-wind interactions, and atmospheric dynamics, play a crucial role in shaping the evolution and composition of gas giant atmospheres. In this article, we'll explore how the composition and density of a gas giant's atmosphere contribute to atmospheric escape and the loss of volatile compounds. Gas giants, such as Jupiter and Saturn, possess atmospheres composed primarily of hydrogen and helium, with traces of other gases such as methane, ammonia, and water vapor. The composition of a gas giant's atmosphere varies with altitude, with lighter gases like hydrogen and helium dominating the upper layers and heavier compounds settling in the lower layers. Thermal escape. Gas giants, with their massive size and intense internal heat, experience thermal escape processes that can lead to the loss of atmospheric gases. Atoms and molecules in the upper atmosphere can attain escape velocities through thermal agitation, escaping into space and contributing to atmospheric loss over time. Genes. Escape. Genes escape occurs when individual gas particles in a gas giant's atmosphere attain sufficient kinetic energy to overcome the planet's gravitational pull. This process is more pronounced for lighter gases, such as hydrogen and helium, which have higher thermal velocities and are more likely to escape into space. Solar wind stripping. Gas giants are subject to interactions with the solar wind, a stream of charged particles emitted by the sun. These particles can strip away atmospheric gases through processes such as sputtering and ionization, particularly in regions of the atmosphere where the magnetic field is weak or absent. Ionospheric escape. Gas giants possess ionospheres, regions of the upper atmosphere where gas molecules are ionized by solar radiation. Ionospheric escape occurs when ions gain sufficient energy to escape the planet's gravitational field, leading to the loss of charged particles into space. Volcanic outgassing. While gas giants lack solid surfaces, they may host volcanic activity on their moons or icy satellites. Volcanic outgassing releases volatile compounds such as water vapor, methane, and sulfur dioxide into the atmosphere, contributing to atmospheric replenishment and loss processes. Gas giants, with their powerful magnetic fields extending into space, are key players in shaping the dynamics of their planetary systems. These magnetic fields not only influence the planets and moons within their gravitational embrace, but also interact with the surrounding space environment, including solar wind and cosmic rays. However, what happens when the magnetic field of a gas giant undergoes reversal? In this article, we'll explore the implications of magnetic field reversal on a gas giant's planetary system and the broader space environment. Gas giants, such as Jupiter and Saturn, possess magnetic fields generated by complex processes within their interiors. These magnetic fields are produced by the motion of electrically conducting fluids, likely metallic hydrogen, deep within the planet's core. The resulting magnetic fields extend far into space, forming magnetospheres that interact with the solar wind and cosmic radiation. Temporal variability. Gas giant magnetic fields exhibit temporal variability, with fluctuations in strength and polarity over time. Periodic magnetic field reversals, where the polarity of the field flips, have been observed on Earth and may also occur on gas giants. These reversals can have profound implications for the planetary system and surrounding space environment. Effects on magnetosphere. Magnetic field reversals can disrupt the structure and dynamics of a gas giant's magnetosphere, altering the configuration of magnetic field lines and plasma interactions. This disruption may lead to changes in radiation belts, auroral activity, and magnetospheric boundaries, affecting the space weather environment around the planet. Planetary protection. Gas giant magnetospheres play a crucial role in shielding their moons and surrounding space environment from harmful solar radiation and cosmic rays. Magnetic field reversals can temporarily weaken this shielding, exposing planetary surfaces and space habitats to increased radiation levels. This poses challenges for planetary protection and the safety of future space exploration missions. Impact on atmospheric escape. Gas giant magnetic fields influence atmospheric escape processes, such as ionospheric escape and solar wind stripping. Magnetic field reversals may alter the distribution and flux of charged particles in the upper atmosphere, affecting the rates of atmospheric loss and the long-term evolution of the planetary atmosphere. Interplanetary environment. Gas giant magnetospheres interact with the solar wind and interplanetary magnetic field, shaping the dynamics of the surrounding space environment. Magnetic field reversals can modulate these interactions, influencing the propagation of solar wind disturbances and the formation of magnetospheric boundaries in the outer solar system. Gas giants, with their vast and dynamic atmospheres, rely on intricate circulation patterns to maintain stability and regulate climate. These atmospheric currents, driven by internal heating and planetary rotation, play a crucial role in shaping weather systems and maintaining equilibrium. However, what happens when these circulation patterns are disrupted? In this article, we'll explore the potential consequences of the disruption of a gas giant's atmospheric circulation on its climate and overall stability. Gas giants, such as Jupiter and Saturn, possess complex atmospheric circulation patterns driven by a combination of factors, including internal heat, planetary rotation, and atmospheric dynamics. These circulation patterns manifest as bands of alternating winds and storms stretching across the planet's surface and extending deep into the atmosphere. Climate variability. Disruption of atmospheric circulation patterns can lead to significant climate variability on gas giants. Changes in wind patterns, cloud distribution, and temperature gradients can alter the planet's climate zones and precipitation patterns, leading to shifts in weather regimes and long-term climate trends. Extreme weather events. Gas giants are known for their extreme weather phenomena, including massive storms, lightning discharges, and turbulent jet streams. Disruption of atmospheric circulation can amplify these extreme events, leading to intensified storms, larger temperature differentials, and more frequent atmospheric disturbances. Astronomical phenomena. Gas giants play a crucial role in shaping the dynamics of their planetary systems, influencing the orbits and interactions of moons, rings, and other celestial bodies. Disruption of atmospheric circulation patterns can affect the gravitational stability of the planetary system, leading to orbital resonances, collisions, or ejections of moons and debris. Atmospheric chemistry. Atmospheric circulation patterns govern the transport and distribution of gases and aerosols within a gas giant's atmosphere. Disruption of circulation can alter atmospheric chemistry, affecting the abundance of trace gases, cloud formation processes, and chemical reactions that drive atmospheric dynamics. Magnetic field dynamics. Gas giant magnetic fields are closely linked to atmospheric circulation patterns, with convective processes generating electrical currents that contribute to the planet's magnetic dynamo. Disruption of circulation can impact the generation and stability of the magnetic field, leading to changes in magnetospheric dynamics and space weather effects. Gas giants, with their colossal atmospheres of hydrogen and helium, exert immense pressure across their vast domains. This atmospheric pressure, generated by the weight of the overlying gases, plays a crucial role in shaping atmospheric dynamics, maintaining stability, and influencing planetary climates. However, what happens when a gas giant experiences a significant decrease in atmospheric pressure? In this article, we'll explore the potential consequences of decreased atmospheric pressure on gas giants. Gas giants possess thick atmospheres composed primarily of hydrogen and helium, with trace amounts of other gases and compounds. The atmospheric pressure on gas giants increases with depth, reaching extreme values in the planet's interior, where temperatures and densities are highest. This high pressure supports convective processes, drives atmospheric circulation, and influences the behavior of atmospheric gases. Atmospheric expansion. A decrease in atmospheric pressure can cause gas giants to expand, with the upper layers of the atmosphere swelling outward. This expansion may lead to changes in atmospheric density gradients, altering temperature profiles and atmospheric circulation patterns. Cloud formation. Atmospheric pressure affects the condensation and formation of clouds in gas giant atmospheres. A decrease in pressure may inhibit cloud formation processes, leading to clearer skies and reduced cloud cover. This change in cloud dynamics can affect planetary albedo, heat distribution, and weather patterns. Atmospheric composition. Atmospheric pressure influences the behavior and distribution of gases and compounds within a gas giant's atmosphere. A decrease in pressure can lead to changes in the mixing ratios of atmospheric constituents, affecting chemical reactions, photochemistry, and atmospheric composition. Internal dynamics. Atmospheric pressure gradients drive convective processes within gas giants, transporting heat and energy from the interior to the surface. A decrease in pressure may disrupt these convective currents, affecting the planet's internal heat distribution and thermal evolution over geological timescales. Magnetospheric effects. Gas giant magnetospheres are closely linked to atmospheric dynamics, with convective processes generating electrical currents that contribute to the planet's magnetic field. A decrease in atmospheric pressure may alter the dynamics of these convective currents, affecting the generation and stability of the magnetic field and magnetospheric interactions with the solar wind. Gas giants, with their immense atmospheres and crushing pressures, are dynamic worlds shaped by the forces of gravity and atmospheric dynamics. The atmospheric pressure on these colossal planets plays a fundamental role in regulating atmospheric processes, maintaining stability, and shaping planetary climates. However, what happens when a gas giant experiences a significant increase in atmospheric pressure? In this article, we'll explore the potential consequences of increased atmospheric pressure on gas giants. Gas giants possess atmospheres composed primarily of hydrogen and helium, with traces of other gases and compounds. The atmospheric pressure on gas giants increases with depth, reaching extreme values in the planet's interior where temperatures and densities are highest. This high pressure supports convective processes, drives atmospheric circulation, and influences the behavior of atmospheric gases. Atmospheric compression. An increase in atmospheric pressure can cause gas giants to compress, with the overlying gases pressing down more forcefully on the planet's interior. This compression may lead to changes in atmospheric density gradients, altering temperature profiles and atmospheric circulation patterns. Cloud formation. Atmospheric pressure affects the condensation and formation of clouds in gas giant atmospheres. An increase in pressure may enhance cloud formation processes, leading to thicker cloud layers and increased cloud cover. This change in cloud dynamics can affect planetary albedo, heat distribution, and weather patterns. Atmospheric chemistry. Atmospheric pressure influences the behavior and distribution of gases and compounds within a gas giant's atmosphere. An increase in pressure can lead to changes in the mixing ratios of atmospheric constituents, affecting chemical reactions, photochemistry, and atmospheric composition. Internal dynamics. Atmospheric pressure gradients drive convective processes within gas giants, transporting heat and energy from the interior to the surface. An increase in pressure may intensify these convective currents, affecting the planet's internal heat distribution and thermal evolution over geological timescales. Magnetospheric effects. Gas giant magnetospheres are closely linked to atmospheric dynamics, with convective processes generating electrical currents that contribute to the planet's magnetic field. An increase in atmospheric pressure may enhance the dynamics of these convective currents, affecting the generation and stability of the magnetic field and magnetospheric interactions with the solar wind. Gas giants, with their swirling atmospheres of hydrogen and helium, are dynamic worlds subject to the forces of internal heat, solar radiation, and atmospheric dynamics. The temperature of a gas giant's atmosphere plays a critical role in shaping atmospheric processes, driving weather patterns, and influencing planetary climates. However, what happens when a gas giant experiences a significant increase in atmospheric temperature? In this article, we'll explore the potential consequences of increased atmospheric temperature on gas giants. Gas giants possess atmospheres characterized by complex temperature gradients, with temperatures varying with altitude, latitude, and atmospheric depth. The temperature of a gas giant's atmosphere is influenced by factors such as internal heat, solar radiation, atmospheric dynamics, and cloud cover. Understanding these temperature dynamics is crucial for deciphering the atmospheric processes that govern gas giant climates. Atmospheric expansion. An increase in atmospheric temperature can cause gas giants to expand, with the upper layers of the atmosphere swelling outward. This expansion may lead to changes in atmospheric density gradients, altering temperature profiles and atmospheric circulation patterns. Cloud formation. Atmospheric temperature affects the condensation and formation of clouds in gas giant atmospheres. An increase in temperature may enhance cloud formation processes, leading to thicker cloud layers and increased cloud cover. This change in cloud dynamics can affect planetary albedo, heat distribution, and weather patterns. Storm intensity. Gas giants are known for their extreme weather phenomena, including massive storms, lightning discharges, and turbulent jet streams. An increase in atmospheric temperature can fuel the intensification of these storms, leading to larger temperature differentials, more vigorous convective activity, and more frequent atmospheric disturbances. Thermal structure. Changes in atmospheric temperature can alter the thermal structure of a gas giant's atmosphere, affecting temperature gradients and stability profiles. This can lead to changes in atmospheric stratification, vertical mixing, and heat transport processes, influencing the distribution of heat and energy throughout the atmosphere. Chemical reactions. Atmospheric temperature governs the rates of chemical reactions and photochemical processes in gas giant atmospheres. An increase in temperature can accelerate chemical reactions, leading to changes in atmospheric composition, the abundance of trace gases, and the formation of atmospheric constituents such as haze particles and aerosols. Gas giants, with their vast atmospheres of hydrogen and helium, are dynamic worlds subject to the forces of internal heat, solar radiation, and atmospheric dynamics. The temperature of a gas giant's atmosphere plays a critical role in shaping atmospheric processes, driving weather patterns, and influencing planetary climates. However, what happens when a gas giant experiences a significant decrease in atmospheric temperature? In this article, we'll explore the potential consequences of decreased atmospheric temperature on gas giants. Gas giants possess atmospheres characterized by complex temperature gradients, with temperatures varying with altitude, latitude, and atmospheric depth. The temperature of a gas giant's atmosphere is influenced by factors such as internal heat, solar radiation, atmospheric dynamics, and cloud cover. Understanding these temperature dynamics is crucial for deciphering the atmospheric processes that govern gas giant climates. Atmospheric contraction. A decrease in atmospheric temperature can cause gas giants to contract, with the upper layers of the atmosphere compressing inward. This contraction may lead to changes in atmospheric density gradients, altering temperature profiles and atmospheric circulation patterns. Cloud dissipation. Atmospheric temperature affects the condensation and formation of clouds in gas giant atmospheres. A decrease in temperature may inhibit cloud formation processes, leading to reduced cloud cover and clearer skies. This change in cloud dynamics can affect planetary albedo, heat distribution, and weather patterns. Storm intensity. Gas giants are known for their extreme weather phenomena, including massive storms, lightning discharges, and turbulent jet streams. A decrease in atmospheric temperature can weaken the intensity of these storms, leading to smaller temperature differentials, decreased convective activity, and less frequent atmospheric disturbances. Thermal structure. Changes in atmospheric temperature can alter the thermal structure of a gas giant's atmosphere, affecting temperature gradients and stability profiles. This can lead to changes in atmospheric stratification, vertical mixing, and heat transport processes, influencing the distribution of heat and energy throughout the atmosphere. Chemical reactions. Atmospheric temperature governs the rates of chemical reactions and photochemical processes in gas giant atmospheres. A decrease in temperature can slow down chemical reactions, leading to changes in atmospheric composition, the abundance of trace gases, and the formation of atmospheric constituents such as haze particles and aerosols. Gas giants, with their vast atmospheres of hydrogen, helium, and trace gases, maintain a delicate balance of atmospheric composition that governs atmospheric processes, weather patterns, and planetary climates. However, what happens when this equilibrium is disrupted? In this article, we'll explore the potential consequences of a disruption in the composition of a gas giant's atmosphere. Gas giants possess atmospheres composed primarily of hydrogen and helium, with traces of other gases such as methane, ammonia, and water vapor. The composition of a gas giant's atmosphere influences atmospheric dynamics, chemical reactions, and the behavior of atmospheric constituents. Understanding the delicate balance of atmospheric composition is crucial for deciphering the processes that govern gas giant climates. Chemical reactions. Disruption of atmospheric composition can lead to changes in chemical reactions and photochemical processes within a gas giant's atmosphere. Alterations in the abundance of trace gases, such as methane and ammonia, can affect the rates of chemical reactions, leading to changes in atmospheric composition, the formation of new compounds, and the production of atmospheric constituents such as aerosols and haze particles. Cloud formation. Atmospheric composition influences the condensation and formation of clouds in gas giant atmospheres. Changes in the abundance of condensable gases, such as water vapor and ammonia, can affect cloud formation processes, leading to variations in cloud cover, cloud properties, and the distribution of cloud layers within the atmosphere. Radiative balance. Atmospheric composition plays a crucial role in regulating the radiative balance of a gas giant's atmosphere. Changes in the abundance of greenhouse gases, such as methane and water vapor, can alter the absorption and emission of thermal radiation, leading to changes in atmospheric heating rates, temperature gradients, and energy transport processes. Atmospheric dynamics. Disrupted composition can influence atmospheric dynamics and circulation patterns on gas giants. Changes in the distribution of atmospheric constituents can affect temperature gradients, pressure systems, and wind patterns, leading to variations in atmospheric circulation, weather regimes, and storm activity. Planetary climate. Ultimately, disruptions in atmospheric composition can have profound implications for the climate and habitability of gas giants. Changes in temperature, cloud cover, and atmospheric dynamics can alter planetary climates, leading to shifts in weather patterns, atmospheric stability, and long-term climate trends. Gas giants, with their powerful magnetic fields extending into space, are key players in shaping the dynamics of their planetary systems. These magnetic fields not only influence the planets and moons within their gravitational embrace, but also interact with the surrounding space environment, including solar wind and cosmic rays. However, what happens when the magnetic field of a gas giant is disrupted? In this article, we'll explore the potential consequences of a disrupted magnetic field on a gas giant. Gas giants possess magnetic fields generated by complex processes within their interiors. These magnetic fields extend far into space, forming magnetospheres that interact with the solar wind and cosmic radiation. The magnetic field of a gas giant plays a crucial role in protecting its moons and surrounding space environment from harmful radiation and charged particles. Magnetospheric collapse. Disruption of the magnetic field can lead to the collapse of the gas giant's magnetosphere, exposing its moons and surrounding space environment to increased levels of solar wind and cosmic radiation. This can have detrimental effects on the surfaces and atmospheres of moons, leading to atmospheric erosion, surface weathering, and changes in geological activity. Auroral activity. Gas giant magnetospheres are known for their spectacular auroral displays, caused by charged particles interacting with the planet's magnetic field. Disruption of the magnetic field can alter the configuration of auroral zones, leading to changes in auroral activity patterns, intensity, and distribution across the planet's surface. Space weather effects. Gas giant magnetospheres play a crucial role in modulating space weather effects, including solar wind disturbances and geomagnetic storms. Disruption of the magnetic field can lead to increased space weather activity, with heightened levels of particle radiation, magnetic disturbances, and auroral displays observed in the surrounding space environment. Ionospheric changes. Gas giant magnetospheres interact with the upper atmosphere, influencing ionospheric dynamics and plasma processes. Disruption of the magnetic field can lead to changes in ionospheric structure, electron densities, and plasma distributions, affecting radio propagation, communication systems, and spacecraft operations in the planet's vicinity. Planetary evolution. Ultimately, disruptions in the magnetic field can have long-term implications for the evolution and stability of gas giants and their planetary systems. Changes in magnetospheric dynamics can affect planetary climates, atmospheric escape processes, and the habitability of moons, influencing the course of planetary evolution over geological timescales.